Good morning. Oh, wow, that's loud. Why is that so loud? How are people this morning? That's better. Right, are people hearing me okay?
Loud and
Good.
clear.
What's that, Patrick?
Loud and clear.
Loud and clear. Great. Well, cross your fingers that technology holds up today. I never figured out what was going wrong. So I'm just gonna plow ahead. So today we're gonna talk about random variables. Last time I made a screencast on Bayes' theorem and some applications of Bayes' theorem. So we're kind of through what we want to talk about as far as computing probabilities by hand and using counting methods. We've talked about conditional probabilities, and that's kind of where the Bayes' theorem comes from. Does anybody have any questions on Bayes' theorem and how it's used before I start talking about random variables? I'm setting up my iPad here too, so that's ready to go. Also, there's the what I'm calling a quiz, but it's really just sort of a glorified homework check. Make sure you're doing what you need to be doing. That that is posted on the Canvas site. Somebody pointed out an error this morning. Charles pointed out that the link to the questions was not working, and that's because I fixed the typo that somebody had pointed out to me and didn't update that link. So that should all work now. And Ashley, yes, the LaTeX source is there too, ready for you to take advantage if you want. I remember messing that up last time.
Thank you.
Keep in mind, yes. Thank you.
I've got a question on Bayes' rule. So
Yeah.
when for type 1 error, is that the probability, is that equal to 1 minus the probability of R complement given D? Or is it just the probability of R complement given D? I was a little confused about that.
Okay, let me, I'm almost ready here with my iPad. It's 8th today. Let me get this. Set up. So you got a question, Patrick, about the Bayes rule stuff as it regards to type 1 error and how to express that as a conditional probability. Did I get that?
Yes.
Okay. So let's throw the old tablet screen up. Okay. Zoom doesn't like it. Okay. So type 1 error is a false positive. So if you've got X is a random variable that represents the result of a binary test. Okay, so like 1 equals true, 0 equals false. And if there's some state that you're testing for, right? If this test is testing for a state, and so we'll say D is the event that the state should be true. Okay, so what's a type 1 error? A type 1 error is where your test, it's a false positive. Test says yes, or test says true, but the state is false. Okay, so the state is false. That would be D complement, right? It's the other condition. It's the complementary condition that the state is true. So a type 1 error looks like it would be the probability that X is true given that the state of the situation should be false.
Okay, that makes sense.
Okay. Good question. Type 1 and type 2 errors will come up again. So this example that I worked for you was a good opportunity to introduce that to you in a context that I think is meaningful, right? These COVID tests and stuff. And it has even become more interesting and more meaningful that now that the President of the United States has started a super spreader event rolling, and we're hearing lots of conversations about, did somebody test positive? Did somebody test negative? Now you have a way to estimate what that means in a probabilistic sort of way. So I think that's kind of a powerful tool that you have. You can be listening to these reports with more of a critical ear. Any other questions on Bayes' rule or conditional probability?
So that would mean type 2 error is X equals 0 given D?
A type 2 error is, so type 1 error is a false positive, and a type 2 error would be a false negative. So that's where the test reports that the condition is false when actually the state should be true. So that would be the probability that X, oops. The probability that X reports everything's, the state is false when indeed the state should be true. So one last fact that I want to leave you with, that it hasn't come up directly in our conversations, but it's come up indirectly. If you have X, a random variable, and E, an event, then we can talk about these conditional probabilities. And this itself, this conditional probability, is itself a random variable. And so these things themselves have to obey the rules of probability. So specifically, the probability of X given E has got to be greater than or equal to 0. And then if you look at all of the events in E and you sum over the probability of all those events, that has to be 1. Okay. So we've talked about this idea of what does it mean for a random, to have a random variable and a probability measure of that, a probability distribution. Okay. What I'm just trying to say is that if you add in conditional probabilities, you create a new situation where you have a new kind of probability distribution that obeys all the rules that we expect a probability distribution to have. So in particular, if if X is a random variable with sample space omega, and then if F is an event in omega, so omega equals F union F complement, then the probability of F given E plus the probability of the complement of F given E, those have to sum to 1. Okay. So here's an example of how we can think of this thing itself as a probability distribution, and therefore it has obeys a rule like that. Okay. So you might have seen that come up in the screencasts I did. If you didn't notice it when it came up, it might be worth going back and looking to see where it did come up, but I didn't want to just totally soft pedal that. Any other questions? Any questions on the problems that I put on that quiz? Okay, I'm not hearing anything. So let's talk about random variables. And I'm going to talk about discrete random variables here. I'm going to limit myself to this type of random variable. And next time I'll talk about some continuous random variables. So what I want to do, my objective here for you today is to show you some special types of random variables, discrete random variables that come up over and over and over and over again. And then I'll try to hook you into some R commands that allow making computing with these easier. Otherwise, you have to compute by hand, and that's kind of a pain. The special random variables I want to talk about are Bernoulli trials, binomial random variables, and Poisson random variables. There's a couple others that I might mention, like the negative binomial distribution, the geometric distribution. They're out there. They're not going to be so important to us, I don't think, but I want to definitely make sure that I talk about these. And then next time I'll talk about continuous random variables that are important to us, like the normal distribution, the exponential distribution, and there might be one more. So let's get going. We only have so much time. So for today, we're going to let X be a random variable, a discrete random variable. For Bernoulli trials and the binomial random variable, X will be finite, but for the Poisson random variable, X is actually going to be infinite. We've talked about this a bunch. Once you have a random variable, you get a probability distribution function. Some people call it a probability mass function. And so I'll abbreviate that PMF, probability mass function, or PDF. And so basically, today I'm going to show you each of these random variables have a different probability mass function. And so when you're asked to understand something about a random variable, usually it's about understanding these probability mass functions. And once we get these probability mass functions, we can talk about their expected value and their variance. And these are things that I talked about in a screencast from last time, I believe. Right? Those look familiar? Okay. An expected value, remember that's a fancy way to talk about the mean, but we'll be fancy where we can. So when you have a probability mass function, recall the definition that I just alluded to it on the previous page. If P of X is a probability mass function for X, then the values of the probability mass function are all between 0 and 1. And then if you sum over all the elements in the sample space, the values of that probability mass function, that adds to 1. Okay. These are the defining axioms for a probability mass function. And you can probably imagine that there's a lot of ways to come up with functions that would satisfy these two conditions. And so today, for each of these random variables, we'll see a different probability mass function. So let's start with the easiest one. We're going to start with Bernoulli trials. Okay, so a Bernoulli trial is a kind of event. So we're going to let X be a random variable with two outcomes. Okay, this is the most important thing. It's got two outcomes, and we'll call these outcomes success and failure. Okay, and we're going to say that the probability that we get a success, we're going to denote that by the lowercase letter p, and the probability that we get a failure, we're going to denote that, its probability has to be complementary, so it's going to have probability 1 minus p. Sometimes textbooks like to denote that as a q. So the probability mass function for this random variable would look like this: P of X equals P if X equals success, and 1 minus P otherwise. Okay, so that's the probability mass function for a Bernoulli trial. You could visualize this random variable and the probability mass function by making a, what do we call it? A bar chart. And the height of those bars would be the proportion of successes and failures. So that's a way we could visualize a probability mass function of a Bernoulli trial. Generally, if I'm thinking like a student, I'm thinking, well, when are these going to come up? How am I going to know if I have a Bernoulli trial? Well, an event or some random experiment is a Bernoulli trial if it only has two outcomes. Okay, and once you recognize something as maybe being a Bernoulli trial, the next thing you need to do is figure out what the probability P is. So we call P here as a parameter of the random variable. This will come up with these other random variables we talk about. And usually you're going to be given a P. And if you're not given a P, you determine it empirically through data. Okay, by looking. So if you're given data, you can look at proportions. If you've got to simulate data, you can simulate data and then look at proportions, and then those proportions will tell you what P is. Can anybody give me an example of an event that would be a Bernoulli trial? A random event that would be a Bernoulli trial? And you can
flipping and getting heads.
What's that, Patrick?
flipping a coin and getting heads.
Yeah. So if X is result of flipping a coin, and then if we say heads is success and tails is failure, that's an example. This is an example of a Bernoulli trial, flipping a single coin. Okay.
Could we make a Bernoulli trial of anything? Because let's say a dice, you either get a 1 or you don't get a 1.
Yep.
Even though there's 6 outcomes.
Absolutely.
Yeah.
So so we could have a random variable be the result of rolling a 6-sided die is 1, right? Then your success is get a 1, and then your failure is get something else, right? And in that framing, yeah, this is absolutely a Bernoulli trial, right? The Bernoulli trial is you get a 1 or not. Good, Daniel?
Yeah, that makes sense. Thank you.
Okay. So in Daniel's example here, what's the parameter P for the probability of success? In Daniel's example of a Bernoulli trial, probability of success for that random variable is
1/6.
Yeah, 1/6. Right? If it's a fair die, right? If all outcomes on the die are equally likely, then the probability is going to be 1/6. So that'd be the parameter for this Bernoulli trial. Back from in the Patrick's example of flipping a coin, if the coin is fair, then either heads or tails is equally likely. So the parameter or the probability of success would be 1/2. You know, my favorite Bernoulli trial right now is the result of a test for the virus that causes COVID. Okay. And so a success of that test, of that Bernoulli trial, I think we all can agree it would be a negative result. And then, I'm sorry, I'm writing so low on the page. A failure would be a positive result. And then what's the parameter for that Bernoulli trial? Well, nobody really knows exactly what the parameter is. But if you look at seropositivity of the American population, right, it's going to be between 2% and 20%. So a reasonable person might say 5%. But that would be a number that we get empirically by looking at data. All right, Shane asked me to go back a page, so I'm going to swipe back for a moment. Let me know when you got what you want, Shane. And I'm going to keep talking. So Bernoulli trial, it's like the simplest possible event that you can have, or simplest random variable we can think of. So now let's ask the question, what is the expected value of a Bernoulli trial? Or what's the mean expected value? Of a Bernoulli trial. And then we'll ask what's the variance. Okay, so I'm going to scroll ahead. So the mean of our random variable, it's the outcome, right? It's the sum of all the outcomes, or sum of all the products of outcome times the probability of that product. So this is our probability mass function. Our sample space, we've got 2 outcomes, right? It's success and failure. So generally for quantitative calculating purposes, we can't go around using words for our outcomes. right? We're generally going to assign these like a 1 or a 0. Like a success will be 1 and a failure will be 0. Right? Because we need to do calculations. I can't do algebra on words. So let's say success is a 1 and fail is a 0. And then, so that's going to be 1 times the probability of a success plus 0 times the probability of getting a 0, getting a failure. And I know my probability of success, that's my parameter P. And then my probability of failure is the complement, 1 minus P. And so 0 times anything is 0. And so I get P. Okay. So the mean of a Bernoulli trial is the probability itself. So what about the variance of a Bernoulli trial? Well, you take the outcomes. So let me write this down as a sum. So the definition is you take the sum over all the possible outcomes of the outcome minus the mean. So this is the distance the outcome is from the mean, and then you square it, and you multiply it by the probability of the outcome. Okay, so this is the weighted, this is the mean of the squared distances. Okay. So for us, we've got 2 outcomes, so I'm just going to write these terms down. One outcome is success, and U is P. We just calculated that above. And the other outcome is failure, which is we're denoting by 0, minus the mean, squaring that, multiplying by the probability of the failure. So am I doing this right? I think I'm doing this right. So I get 1 minus P squared times P plus P squared times 1 minus P. And again, I'm sorry, I'm so close to the bottom. I'll continue at the top here. Looks like I can pull out, I've got a P in both terms and I got a 1 minus P in both terms. So I can pull those out to simplify. And I'm left with a 1 minus P from the first term, and I'm left with a P from the second term. And look at that, holy smokes. Those suckers cancel. And so I'm left with P times 1 minus P. So if X is a Bernoulli trial with probability P, the mean of the random variable is P, and we'll write the variance using the Greek letter sigma squared is P times 1 minus P. And so the standard deviation is the square root of P times 1 minus P. Okay. So this is the kind of description I want to generate for all these random variables that I'm going to tell you about today. Okay. Let's look at it, just calculate a couple things. Let's look at a fair die, or fair coin flip. So say X is the result of flipping a fair coin and hoping for heads. So success is you get heads, a failure is you don't get heads. Okay, so we're going to assign 1 to be the outcome for heads and 0 to be the outcome for the complement. So fair means either outcome is equally likely, so the probability of getting a heads is a half. So what's the average? What's the mean of this random variable? It's 1/2. And what's the variance? Well, it's 1/2 times 1 minus 1/2, 1/4. And so the standard deviation, the standard deviation is 1/2, the square root of 1/4. So if you think about this in terms of a plot, a bar plot, You've got your relative frequency bar plot here. Your mean is right in the middle. And then your standard deviation takes you all the way down. So mu minus the standard deviation is 0, and mu plus the standard deviation is 1, right? So you go all the way down to the lowest possible value, or all the way up to the highest possible value. This is kind of remarkable that this is showing you that your spread covers your whole sample space. Okay. Let's just play. Let's suppose it's the same random variable as before, the flipping the coin. But let's suppose it's not a fair coin. But let's suppose P is biased slightly toward tails. So what would be a probability that's biased slightly towards tails? Let's say 13/24, 11/24. Okay, slightly less than 1. Okay, so our mean in this case is going to be 11/24, and then our variance is going to be 11/24 times 1 minus 11/24. That's 11 times 13. Oops. Over 24 squared. Okay, so that's, what is that? 143 over 24 squared. Let me get a calculator. 143 divided by 24. Oops. It's about 24.248, which is about what the variance was for our fair example. Now let's calculate the square root of this. Yeah, the square root's about 0.498. So the standard deviation is about the same, a little bit smaller. So if the chance of the getting tails is slightly bigger, so I tried to draw the height slightly higher there. The median, or the mean rather, if this is a half, the mean is slightly over this way. And the standard deviation, mu plus sigma, that's definitely less than 1. And mu minus the standard deviation, (11/24) is about 0.458. So you subtract the standard deviation from the mu, and you get a number that's less than 0. Oops. So that definitely clears the whole sample space. Anyway, this is an effect of changing your probabilities a little bit. It shifts the balance in your probability distribution. All right, that wasn't terribly interesting. Let's talk about the next. Are there any questions about the Bernoulli trials? They're simple. They're a building block, and they lead us directly into the next random variable called the binomial random variable. So I'm going to give you a fact, and it's a fact. It's really a theorem. It's called the binomial theorem. You may have seen it before. You may not have seen it before, but you certainly have worked with it. If you take two numbers and you add them and you raise them to the nth power, right? you get all kinds of combinations of the powers of x and y multiplied against one another. And I'm going to use sigma notation to write down what you get. So you're going to get x to all these powers between 0 and n times y to the n minus k powers. So the powers, or the exponents here always add up to n. So these are going to be all the terms of your polynomial of two variables. And then the coefficient you get here is n choose k. So it's a really pretty cool theorem. And you'll see in a minute why this binomial random variable has this, is called what it is. So let's let x be a random variable that represents the number of successes of n Bernoulli trials. Which have a probability p of success. So like flip a coin 10 times. So what is the probability you get exactly 5 heads? That would be measured by a binomial random variable. The probability you get 5 heads. If x is the number of SARS-CoV-2 tests given at a testing station, and if a test has a probability p equals 5%, which is 0.05 of coming back positive, we could ask, what's the probability that 86 tests come back positive if 500 tests were given? Okay. This is a binomial probability. This is represents a binomial random variable. If x is the number of positive tests that come back, if you administered 500, that's a binomial probability. Here, and I'll give you one more example of a scenario that would be modeled by a binomial. So suppose you work for a company that produces widgets at its factory. And on the production line, a widget has a 1% chance of being defective. And that chance is independent of what the quality of other widgets. The line can produce 180 widgets a day. So if we let x be the number of defective widgets, on a given day, then X is a binomial random variable with parameters 1% and n equals 180. Okay, so here binomial random variables happen all the time. Okay, they're all around us, so it's important to know how to model these things. So the first question we ask is, this is great, what's the probability mass function? For a binomial. And we can kind of answer this pretty easily by using the principle of multiplication. Note that the Bernoulli trials are independent. Okay, so this allows us to use multiplication to compute probabilities. So if we have n trials, and each one of them can be a success or a failure, and we want k successes, that means n minus k failures. What's the probability of getting k successes? Well, if one success has probability p, then k successes has probability p to the k, right? Because you have to have the first is a success and the second one is a success, so that's p squared. And the third one is also a success, so that's p cubed, and so on and so forth. At the same time, you want exactly n minus k failures. And so what's the probability of that? Well, that's p to the n minus, well, not p, right? Probability of a failure is 1 minus p. So the probability of n minus k failures is 1 minus p quantity to the n minus k. And what's the probability these happen at the same time? Well, you have to multiply them because they're independent. So the probability that we get exactly k failures out of n trials is going to involve this number. Let me go to the next page. I'm going to write this down. Probability of k successes in n Bernoulli trials. With success probability p. Okay. It's going to use the term p to the k times 1 minus p to the n minus k. Okay. So this is the probability that one specific trial, like if you look back at my pictures here, I wrote down the first k trials were successes and the last n minus k trials were successes. But I don't care about the order, right? And if I don't care about the order in which these occur, I need to go count how many different ways can I have k successes among n minus k failures, right? How many ways can I put a success into these n slots? And that's exactly n choose k. So the probability that my n Bernoulli trials have exactly k successes is n choose k times p to the k, 1 minus p to the n minus k. So I claim that this is our probability mass function. Okay. And so to convince you of that, I just have to show it satisfies two properties, that it satisfies that all the terms, the function is always positive and less than 1. And then I have to show that the terms sum to 1. Okay. So I'm going to show that for every possible outcome, my function is positive. Right? And so notice the possible outcomes are the numbers 0 to n. So for every possible k, the probability I have k successes in n trials is bigger than or equal to 0. But this is obvious. This is obvious because if you look at the formula that I'm using, n choose k is always positive, p is positive, and 1 minus p is positive because p is between 0 and 1. So I'm multiplying a positive times a positive times a positive, and so my probability is going to be positive. There's a chance, sure, that my p could be equal to 1, so this whole thing is 0. But I'm only interested in my probability mass function being bigger than or equal to 0. Okay, so obvious. I satisfy that one property. So next, I want to prove that if I add up all my probability mass functions, I'm going to get 1. Okay. So to show you that, I'm going to move to the next page, and I'm going to recall that binomial theorem for a second. So the binomial theorem says, take two things and add them and raise them to the nth power. And that's the sum as k goes from 0 to n of n choose k times x to the k times y to the n minus k. Okay, so we want to show that the sum over all outcomes in our sample space of our probability mass function equals 1. So our probability mass function is n choose x times p to the x times 1 minus p to the n minus x, where x is an outcome. That's the definition I brought to you. Now let's write this in a more familiar way. Since omega, my sample space is the number of, or consists of the numbers from 0 to n. I'm just going to rewrite this in this way. And then I'm going to draw your attention to the binomial theorem. So look at this and look at that. Our summations are the same. We're going from 0 to n. So that's good. We've got choose notation here, exactly the same. The exponent on the x and the p, they coincide. And the exponent on the 1 minus p and the y, they coincide. So this suggests that in the binomial theorem, I should put x equal p, and I should put y equal 1 minus p. That is to say, I can use the binomial theorem on this expression where x is p and y is p, or 1 minus p. So doing that, the binomial theorem tells me this huge summation can be simplified as the quantity p plus 1 minus p to the nth power. And that minus p cancels with that p, and I get 1 to the nth power, which is 1. And that proves that these expressions add up to 1. And so indeed, I have a probability mass function. These things, these crazy looking things are my probabilities. Okay. So this was step one. Once we identified the binomial theorem, now I've given you a formula for the probability mass function. And now we can use that to do stuff. So let's talk about Patrick's favorite example. Let's say we're flipping coins. What is the probability of getting heads? Exactly 4 times if I flip a coin 10 times. All right, so let's answer this question. This experiment of flipping 10 coins and counting the number of heads, this is a binomial experiment. This follows a binomial random variable. So X is binomial with probability 1/2, assuming it's a fair coin. And if it doesn't say otherwise, we'll assume it's fair. And the number of experiments N is going to be 10. And we're interested in K equals 4 successes. So the probability mass function, well, let's do it this way. Is N choose K, P to the K, 1 minus P to the N minus K. So for us, we know what N, P, and K are. We want to calculate P of 4. Our N is 10. P is 1/2. K is 4. P is 1/2. N minus K is 10 minus 4, or 6. Oh, look at that. Well, both our bases are 1/2, so I can use the law of exponents and put those things together. So I get 10 choose 4 times 1/2 to the 10th power. Okay, so what's a good way to calculate this? Well, we can calculate it by hand. So we get 10 factorial over 6 factorial times 4 factorial times 1/2, or times 1 over 2 to the 10th power. I'd like a decimal representation for that. So I'm not happy with what I'm looking at here. It doesn't make me feel good. So we want to turn to R. Wouldn't it be great if we could use R to do this? So in R, in choose K, you can calculate that with the choose function. So we'd say choose N comma K. So for us, we type in choose 10 comma 4. And I'm going to type that in right now. And R gives me 210. All right. And then I'm going to type choose 10 comma 4, and I'm going to multiply it by 1/2 to the 10th power. And that's a really small number. But choose 10 comma 4 times 1/2 to the 10th is approximately equal to 0.2050781. So that's what R gives me. I think I could do this. I think there's a command dbinom of 4. Let's see if this gives me the right thing. There's another command called dbinom, right? Binom refers to the binomial distribution. D refers to the distribution, right? We're looking at the distribution mass function. So dbinom and its parameters are K, and then you put in size equals, and then your number of trials, and then you put in probability equals P. So for us, we want to type in D binom 4, comma, size equals 10, comma, prob equals 1/2. And if you do that, you get 0.2050781, which is exactly what we expected to get. Okay. So the point I'm trying to make with you right now is you need to know what formulas that we use, or you need to know, I mean, really, you need to know what random variable to use to model a phenomenon. Once you know what random variable to use and the parameter values to use, you don't need to worry about this formula for the probability mass function. I hope you do, because they're beautiful, but you don't, because R will do it for you. You really should know this, okay? So for calculation purposes, let's lean on R. And I think that's going to be the most important thing in this class. For cultural and mathematical enrichment purposes, it's good to know this. I will not ask you to memorize this, but I will ask you to be able to know where to find this formula if the need arises, and how to use this formula, okay? Because at the very least, all math students, they should know how to check their work. So you make a calculation in R and you should never trust it, all right? Sometimes you have to trust it, but if you get a choice when you're learning something, you shouldn't trust it, right? I felt good about this because I got this number and it matched that, right? And I knew how to calculate, I knew to execute this in R because I knew this formula, okay? So it allowed me to kind of triangulate onto the right solution. So let this problem here that we work through be a model for how you think about how you can use R and learn this stuff. Again, let me repeat. And most profs wouldn't do this, but this is what I'm going to do right now. Don't have to memorize this, but you got to know where to find it when you need it, okay? Because this will inform you doing that kind of stuff in R, right? But I really do want you to know about this. And when you're using R, you never have to memorize anything. You can, there's always the help function. So if you forget how to use the dbinom command, just type in $D binom with no space between the question mark and the D, and then the help browser will open up and tell you how to use it. Okay. So let's do a variation on the previous problem where we're flipping 10 coins. Let's ask this question. What's the probability I get no more than 4 heads? If I flip a coin 10 times. Okay. So what's the probability that I don't get 5 or 6 or 7 or 8 or 9 or 10, right? What's the probability that I get 1 or none, 1, 2, 3, or 4? Okay. None, 1, 2, 3, or 4. So this is the probability. I'm asking, what's the probability that my binomial random variable is less than or equal to 4? Okay. So the thing you need to remember is we need to calculate all these separately. So the probability that I'm less than or equal to 4 is the probability that I'm 0. Well, here, let's write it this way. Oh, I'm going to write it in English. 0 or 1 or 2 or 3 or 4. Okay. And these are all mutually exclusive events. None of them can happen simultaneously. So the laws of probability tell us that the probability that one of these happens is the probability that 0 happens plus the probability that 1 happens plus the probability that 2 happens plus the probability that 3 happens plus the probability that 4 happens. Okay? That is to say, it's the sum as k goes from 0 to 4 of the probability that k happens. Oops. So let's calculate that. So I'm going to swipe back a page and point something out to you. Technically, like if you were growing up with me, like way back in the day, I would go and grab that formula, bring it over, and plug it in there. So I've got 10 choose k times 1/2 to the k times 1 minus 1/2 to the 10 minus k. And I'd have to work this out. But let's use R, right? R is the way to go. There's a bunch of cool algebra I could do to simplify this, but eventually I'm going to have to do some calculation. What would R do? Okay. So to make R do this, I want to point out that this stuff right here is just the that dbinom command. So we'd have dbinom k, and then the size of the group would be 10, and the probability is 1/2. Okay, I think we can. I'll test this to make sure that this works. Notice what I'm not putting in that size equal 10, and I'm not putting in prob equal 1/2. So I'm going to see if this works. See if you don't have to put those in. But here my k is an index, right? It's going from 0 to 1. And so what you do with R is this. So you say let k, and you do this assignment operator. And we're going from 0 to 4. And so you put 0, comma 4. Or, sorry, colon 4. That's the same thing as making a vector that consists of those counting numbers. So k is now the vector 0, 1, 2, 3, 4. And then you can type this, and I'm going to have to do this across a couple lines. The sum of dbinom k, comma 10, comma 1/2. And here, that k is referring to this k. And so it's going to sum over all the possible values of k, these values of the binomial. So this, let me do this in a different color. This is the R expression of this. Okay. So give me a second here. I'm going to type this in to make sure it works. I'm going to type in k assignment operator 0, colon 4. Okay, R does not puke. Then I'm going to type in sum parentheses dbinom parentheses k, comma 10, comma 1/2. And hit enter. And R tells me we get 0.376951. Okay, so let's just check to make sure R is doing what we hope it's doing. Copy this. I've got 10 more minutes. Copy and paste that. Ooh, what's that? So I'm going to calculate dbinom. Oops. So in K, I'm just going to calculate. I'm going to use the binomial command. This is what I get when K is 0. What's the probability that you get no heads? What's the probability you get one head? What's the probability you get two heads? What's the probability you get three heads? And what's the probability you get four heads? And if you look at those numbers, those individual numbers, it looks indeed like they sum up to that number. So this summation formula, the summation way of doing it seems to work. Okay. So there's a tool in your bag of tricks for using R to calculate probabilities for binomial functions. Yeah, that should be very useful to you. Let's go on to talk about mean and variance of a binomial distribution. So I'm not going to go into the details about this because the proof is a little bit technical. It's kind of neat, but it's a little bit technical, and it's beyond what I really want you to be concerned about for this course. But let me show you how the formulas work. So we're going to let X be a binomial random variable. Oops. With parameter P. And total number of trials N. And I want to know what's the mean? What's the expected value for this random variable? Well, we know that the expected value is the sum over all possible outcomes of the outcome times the probability mass function, the probability of that outcome. Okay. So written in another way, it's the sum over all the outcomes of the outcome times the probability that my random variable attains that outcome. So let's rewrite this one more time. Our number of outcomes, right? That's the number of successes in N trials. So the number of successes go from 0 to N. They're the counting numbers, right? And so this is the formula for my mean. And I'll take it one more step. Well, two more actually. Use the formula for my mass function for this probability. Now it turns out and this is what I'll do in a screencast. I'm not going to do it now. This sum actually simplifies to N times P. So the expected value of a binomial random variable is the number of trials times the probability of a success. Okay. So that's the central tendency of a binomial random variable. So it could be fun to generate a simulation of a binomial random variable and have N be really big and look to see if the mean, like the middle of that distribution, seems to be piling up around N times P. And I guarantee that it will. So what does this tell us? So suppose I flip a coin 10 times and it's a fair coin. How many out of those 10 times do I expect to see a heads, right? That's a question about an expected value. You know, what do I expect a binomial random variable of N trials with a probability of success 1/2? What do I expect the outcome to be? Well, it's the number of trials N times the probability of success, P is 1/2. 10 times 1/2 is 5. So if I'm flipping a coin 10 times, I expect it to land heads 5 times, right? That's a computation. If part of you is sitting here saying, no, duh, you're speaking from your lived life and your empirical experience of flipping fair coins. And the fact that you're saying no, duh, should be, oh, wow, that does say what I think it says. That does say what my experience says it should say. Okay. All right. What about variance? The variance of X, okay, that's the sum over all the possible outcomes of, oh yeah, this is gonna be gross, of the outcome minus the mean squared times the probability of the outcome. So I'm just gonna write this as the sum as k goes from 0 to n of k minus n times p, quantity squared, times n choose k times p to the k times 1 minus p to the n minus k. So this is the expression in all its glory to calculate the variance. What I want you to know is that this simplifies to n times p times 1 minus p. Okay, that's the variance for a binomial random variable with parameters n and p. Variance is often written as this sigma x squared. So the standard deviation, sigma x, is the square root of this. Okay, so that's what I want you to know about the binomial random variable. And I'll give you some problems to practice on that involve calculating standard deviations and things of binomial random variables. So the last probability distribution that I want you to know about, and I'm not going to have time to talk about it in depth, so I'll just do a screencast. It's not, I don't think it's hugely important, but it's the Poisson distribution. It's fun to say. Poisson, nice French word. So it's a distribution that it goes with a random variable whose sample space is infinite. Okay. And this random variable is a Poisson random variable with parameter lambda if the probability mass function looks like this. The probability of the random variable having a result I equals e to the minus lambda times lambda to the ith power over I factorial. Okay, and this is for I, all the i's that are in the sample space. And so I guess it's worth saying that lambda has to be a positive number. So is this indeed a probability mass function? Yeah, it's a probability mass function because all of these things here are positive, right? E to the minus lambda, that's a positive number. Lambda is a positive number, so positive to a power is positive. Factorials are always positive, so this is always a positive number. And to see that they add up to 1, take a look at this. So we're going to sum over our whole sample space, so that's the infinite number of numbers, e to the minus lambda times lambda to the I all over I factorial. Now, this e to the lambda can come out. I'm going to go to the next page. We can pull the e to the lambda out because it doesn't have an index in it. Okay. Now, your Calc 2 siren should be going off because you see that this right here, this is an infinite series. And if you do the ratio test on the terms, you'll see that this series converges. Okay. Not only does it converge, if you remember, x to the n over n factorial, as n goes from 0 to infinity, right? This is a power series representation for the function e to the x. So what we have right here is basically lambda to the, or e to the lambda. That series converges to e to the lambda. And e to the minus lambda times e to the lambda is e to the minus lambda plus lambda is e to the 0, which is 1. Okay. Yay, power series. So I'm going to stop here with this and just I'll make a short screencast about the Poisson distribution. And what I'll say is that Poisson is like the binomial. Okay, Poisson has one parameter, binomial has two parameters. There's a way you can use this Poisson distribution to approximate a binomial, and I'll put that in a screencast. I don't think it's critical for us, but it's good to know. So with that, I will say thanks for being here. I'm glad Zoom didn't crap out on me. Yeah. Any questions or comments before we call it a day?
Yeah, Dr. Miller, could you go back to the previous tweet for like a couple seconds, please?
Yes, let me reshare it and I will go back. Can you see it, Sitlali?
Yeah.
Okay. Anything else? Anybody else want?
Okay, thank you.
You bet. Okay, thanks everybody. I will see you online. Yeah, take care, stay healthy. Talk to you Tuesday.